Welcome back. So today is our last set of online classes. I'd like to finish up our unit on thermodynamics, and then before we do that, I'd like to remind you about the assignments you have left to do. So first of all, you have one more homework assignment, so that's due on Monday, May 3rd at 10 o'clock. You also will have a extra credit homework, so we haven't opened that up as of right now, but that will be due on Tuesday, May 11th at 10 a.m. The extra credit homework will either replace your second lowest homework grade, or it counts as a 5% bonus to your homework score, whichever improves your grade the most. The extra credit homework will be posted to the homework directory on Long Kappa. So also then you have this classwork assignment, so that's going to be due on Friday. So for next week, we will run the Zoom classes, but there we'll go over old material. We won't be doing anything new there. And so last, for the final exam, so that is going to be through the Respondus Lockdown browser, and it'll be just like the midterm. The exam is on Tuesday, May 11th, and it'll run from 9 a.m. to 8 p.m. The exam is timed for 3 hours, and it will be about 40 questions. The exam will be cumulative, so material from the first half of the course is fair game, and in fact will make up about half of the exam. You can use a scientific calculator and a blank scratch paper, but smartphones are expressly forbidden. Okay, so be aware of these upcoming assignments, and good luck with them. So, one of the most important applications of thermodynamics is the heat engine. Turning work or kinetic energy into heat is pretty easy. If you stir a cup of water with a spoon, the work that you do raises the temperature of the water by just a little bit. Actually, whatever you're doing right now, if you are moving in the slightest, well, congratulations, you are converting work into heat. However, if you want to do the reverse, you need to convert heat into work in a consistent way, well then that requires a bit more thought. What we would like to do is to make a heat engine. The goal of a heat engine is to convert heat into work with no other change taking place in your system. I'm showing you a schematic here of a heat engine on the left. Heat flows from a high temperature reservoir to a low temperature cold reservoir. By reservoir, I really just mean that you have a high temperature source that heat flows from, and if you have a flow of heat, then you need something colder for that heat to flow to. Now we would like to convert some of that heat flow into work. When we say we want no change in the system, that means we would like the internal energy of the working system to be unchanged and be the same after the process is finished. We would like an engine that in principle can run for an extremely long time. You put in heat, you take out work, and continue to do that. If the internal energy is lost in the process, then you can only run until you're out of internal energy, and then, well, you're done. So, using the first law of thermodynamics and the fact that the change in internal energy of the engine is zero, then the heat into the engine from the high temperature reservoir must equal the heat out to the cold reservoir plus the work done. The purpose of an engine is to transform heat from the high temperature reservoir into work, so we measure the success of an engine using the efficiency of an engine. The efficiency is the amount of work you get out of the engine divided by the total flow of heat from the high temperature reservoir. So the efficiency is the work divided by QH, and so then we can rewrite this, since work is equal to QH minus QC, to be QH minus QC divided by QH is equal to the efficiency. So to maximize the efficiency, we would like the heat flow to the cold reservoir to go to zero. It turns out that a heat engine with an efficiency of 1 or 100% is impossible, but it gives us a way of measuring the success of our engine. In order to understand how engines work, we need to be able to put our engine through a cycle. That means we need at least 2 different processes so we can return our engine to its original pressure, volume, and energy. The first process we'll look at is an isotherm. In an isothermal process, as the name suggests, the temperature is held constant. So if the temperature stays the same, then we can use the ideal gas law, and that tells us that the pressure at point 1 times the volume at point 1 is equal to the pressure at 2 times the volume at 2. So we can calculate the change in pressure and volume. We can use this to find the work done by an isothermal process. The work done by the gas is nRT times the natural log of the final volume over the initial volume. This symbol ln, so this represents a natural logarithm, which is a logarithm to the base e, where e is the mathematical constant that's approximately equal to 2.718. To find this on a scientific calculator, you can press the ln key and then enter the number you want to find that natural log of. When the volume of an isotherm increases, then the gas does work, so the work done is positive, and when the volume of an isotherm decreases, work is done to the gas, and so the work is negative. I should note here that if the natural log of something is greater than 1, then the natural log is positive, and if you are taking the natural log of something that is less than 1, then the natural log is negative. If the gas expands, it has done work, and that makes sense, but in an isotherm, as the name tells us, the temperature stays the same. How is that possible? During an isotherm, the work done by the gas is exactly equal to the heat added to the gas. When the gas expands, it should cool down, but we add heat to the gas, so the temperature stays the same while it expands. During a compression, the volume decreases, so the work done by the gas is negative, and as that happens, it should increase the temperature. It does not increase because heat flows out of the isotherm, maintaining the same temperature. The reason for this is that in an isotherm, the internal energy of the gas is held constant, so from the first law of thermodynamics, Q, the heat flow, and the work done must be equal to each other. In order to build an engine, we need two different processes. So our second process is called an adiabatic process. In an adiabatic process, the heat flow is zero. Adiabatic processes are pretty common. If you have a fast expansion or compression of a gas, it often happens so quickly that we consider the heat change to be zero, so we can treat the process as adiabatic. Also, if your system is well insulated, then the heat flow is very small, so again you can treat the process as adiabatic, as if no heat flows into or out of our gas. The adiabatic process is a bit more complex than the isothermal. To solve the change in pressure and volume, you need to know the heat capacity of the gas, since you are both doing work and changing the temperature. In any case, what we need to know is that the work done in an adiabatic process is equal to N times the constant volume heat capacity times the initial temperature minus the final temperature. In an adiabatic expansion, if the temperature increases, that means we have compressed the system and done work to it, so the work done by the gas is negative, and if the volume has decreased. If the temperature has decreased, then the gas has expanded, so the work is done by the gas, and the work is positive, and the volume increases. The heat, of course, is zero in all of these, so the Q for all of these systems, for all of these adiabatic processes, is zero. Essentially, in an adiabatic process, we are converting temperature into work when it expands, and when it is compressed, we are converting work into higher temperature. So now we can put the full cycle together. We start at A, and our gas undergoes an isothermal expansion at the temperature TH, the temperature for a high temperature heat source. As the gas expands, it does work. Once we are done with our isothermal expansion, we now do an adiabatic expansion. Work is also done here, and the work done by the gas as the gas cools down, and the gas cools to the temperature of the low temperature reservoir. We now do an isothermal compression at this lower temperature. Notice as work is done to the gas at this low temperature, heat flows from the engine to the cold source. Once that's done, we compress the gas adiabatically to raise the temperature back to that of the high temperature heat source. Notice that we have gotten back to exactly where we started, so this cycle results in no change in the internal energy of our gas. Also, net work is done. We can see that as the cycle does more work on the expansion than the work is done to the gas in the compression. This is because the compression happens at a lower temperature than the expansion. So we'd really like to know how much work is done in this process. If we look at the adiabatic process, the work done is proportional to the change in temperature, and since the change in temperature is the same, no net work is done by the adiabats. All of the net work is done by the isotherms. So we can find the work done by the isotherms and get the net work, and then we divide that by the heat added from the hot reservoir. When we do that, we get the efficiency of a Carnot engine, and we find that efficiency to be 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. It turns out this is the largest physically possible efficiency for an engine operating between two temperatures. The reason for this is that all of the net work and heat flow is done by isotherms, so the processes that do the work are operating at the highest possible temperature, and the compression is working at the lowest possible temperature. It also means that the temperature difference sets the possible efficiency. If the temperature of the hot and cold reservoir are the same, then the efficiency goes to zero. It also means that the colder the cold reservoir, the more efficient the engine. The key is that you want a larger temperature difference. This should sort of make sense. For most engines, the cold reservoir will be room temperature or a bit higher, so you want the engine to be as hot as possible to maximize the efficiency. Okay, so we have a question to do here. So what is the efficiency of a Carnot engine operating between 100 degrees Celsius and 520 degrees Celsius? Well, the main thing that trips people up on these questions is converting from Celsius to kelvins. So to find the efficiency, we use that the efficiency is equal to 1 minus T cold over T hot. That is equal to 1 minus T cold is 100 degrees plus 273 to get 373 kelvins. Then we divide that by 520 plus 273, which is 793 Kelvin. So 1 minus 373 divided by 703 gives us an efficiency of 0.53 or 53%. That means that if we put a certain number of joules of heat into this engine, then 53% of that would be converted into work. So we would multiply the energy put in times this efficiency to get the work done. All right, so you have a few questions to do with this, and next we're going to take a look at the second law of thermodynamics.